Today we are going to do section 3.1, vector valued functions. Now, what is a vector value function? Well, normally we know what a vector is, right? Vector is just three numbers here, which represents the three components that in space, x1, x, y, and z components. Now, suppose you have a function in here, okay? That each one has its own function, so that is going around in space, okay? So that would be called a vector function. And that we will call it, say, the first function, the first direction, in the I direction, we have f of t, and j direction, we have g of t, and that would be a 2D vector. If it's a 3D vector, you have a third one, the k direction, with an h of t, and it can also be written like this, whether it's just two of them in 2D or three of them in 3D. So that is the definition of a vector function. As you can see, a vector function is just like a regular function, except there's three of them, which makes it 3 times as much work. And with that, but otherwise, other than being 3 times as much work, it's no harder than any function that you've done before. And we're going to deal with them exactly like 1D, like the normal functions we've done, which were in 1 dimension. And now we're going to do 3 dimensions with 3 functions at a time. So with that, please do example 3.1. And then, which is to evaluate some of this. You evaluate it just like any other function. And then next, example 3.2, to graph something. Now, to graph these vector functions, let's just, well, you can look at what the book does, which is finding points and try to plot it in space. Let's just do it in Desmos 3D, which we have done a couple of those already in the previous section, and this is no different. You type the thing in there, and then you adjust the value of t until the whole thing is properly drawn, and that's how you do this type of thing. And the Desmos calculator does a really good job of it too. And everything looks totally beautiful. So as you can see, next there is one in example 3.2c. Okay, you're drawing some what is that, helix or something? Well, we don't care, a spiral. Yeah, actually they call it a helix, which is fine. Then you draw your spiral and see how it spirals up. It's all very, very nice. And it doesn't take very long to do that in a calculator, of course. So please do examples 3.1 and 3.2 as part of your homework. Next, let's look at page 266, and let's consider now limits and the continuity. So we're going to finally do calculus. Okay, the limit. What is the limit of a vector valued function? It is defined as this. If this is a vector function, remember a vector function has 2 or 3 parts, and it will approach a vector. This is not a number. This is a vector called L. It approaches L as the t approaches a if the magnitude of the difference vector approaches 0. And how you're supposed to do that? Well, as it turns out, that means that each component of these things is going to approach the limit. Okay, that is, f of t will approach L1, and g of t will approach L2, and h of t, if it's there, will approach L3. So all 3 limits will approach at the same time, which is as listed in theorem 3.1. As you can see, they said, how do you calculate the limit? The limit is you work on each function, each component function, so that each one approaches where it's supposed to go. And you know what that means? That means when you're calculating the limit of the vector, you're going to be doing 3 limits for the price of 1, okay? Which is tedious, probably, but that is the way it is. And being that we're doing limits now, so yeah, you have to do 3 times the work. And with that, please do example 3.3, which is identical to anything you've done in Calculus 1 back when you were doing limits, except that now you have to do 3 times per problem. So please give yourself a little more time to do vector calculus, because you got 3 parts to think of. Now, it's not the good old days when you had only 1. Now you have 3. So you got to feed them all. Anyway, so please do example 3.3 as part of the homework. Now, besides being 3 parts, there is no difference whatsoever from limit of just one function. Next, let's look at page 267, where we have the definition of a continuity of a vector function. Now, what is a vector function? Is some line in space, okay, like the helix we saw earlier. And how is it continuous? Well, it is continuous exactly the way you would imagine. It means not broken. Part of it didn't suddenly go off to infinity or something like that, or it just simply broken, called a jump continuity. That is, it broke for no reason at all. It just stopped here and then took off somewhere else. Anyway, so however, a vector that is called continuous if 3 condition holds, okay, and let's read the definition first. It has to exist there, yeah, no kidding. Number 2, the limit at that point also exists. And number 3, the limit at that point equals to the point itself. That is, as you get close to it, it better be the value, okay? Because when people get close to it and there's a cliff and the value is somewhere else, then it's broken. It's not continuous anymore. And that is true whether the vector is a 2D vector or a 3D vector. So having said that, that's the end of this section, I guess. All right, so being that you have to do 3 times the work, the section is fairly short, I guess, so that you don't have to wear yourself out as much. And therefore, please do homework. And part of the homework says something about the orientation. Now, what is the orientation of the curve, which I did not notice the book mentioning, so I will mention it quickly. The orientation is when you draw a curve on the Desmos calculator or anywhere, and as t increases, then you will see the curve increase. Okay, for example, might be like this. This is where t is 0, and that's t is something else, like 1 or something. So the orientation is the direction of t's increase. And that is what they want. If you see a homework asking you which way, please mark the orientation of your curve. You just figure out which way the curve is going. And on the calculator, if you can't tell which way it's increasing, you can just reduce the value of t in Desmos by, say, start at 1/2 and then go to 3/4 or something like that and see how the curve increases. Then you know which way the arrow should point. Now, so please do homework. There's not that many homework worth doing in this section because we're just a quick introduction, really. So please do problems 3, 7, 13, 17, 19, 21, 25, and 27. And that marks the end of this section.